Rational drug design is the process of finding new medication that can activate or inhibit the biofunction of a target molecule by binding to it and forming a molecular complex. Typically, between the ligand drug molecule and the target must exist complementarity in terms of shape to result in high affinity and charge to result in a specificity. To come up with a good ligand for a receptor, a huge pool of candidates must be screened one by one, and perhaps the most reliable way to do so is through experimental investigations. However, purely experimental screening is exhaustive in terms of labor, time, and most importantly, cost. In fact, it is preferable to use a virtual screening tool to narrow the wide range of candidates down to a small set of the most promising solutions, and then employ experimental screening methods to further investigate those solutions to come up with something that really works. The tools developed for this purpose can be categorized into two classes of computational and physical. Each category has its own strengths and weaknesses. Physical tools offer tangible experience of the molecular interactions, but they lack measurement and evaluation capabilities. On the other hand, computational tools enable accurate and fast evaluations. However, they do not deliver an interactive, tangible experience. We have combined and enhanced the unique, strong features of physical and computational tools to develop a hybrid tool, so-called as Assemble and Match, comprised of physical and computational modules. The computational module or software has itself two submodules, one for design and another for analysis. The input in the form of biostructural information from protein data bank or some customized molecular model is fed to the design module to generate the CAD models of the ligand fragments and the receptor target. These CAD models are then printed using a 3D printer to yield the physical models of the ligand fragments and the receptor. The user then will exploit their visual and tactile sensory as well as their geometric intuition to assemble the ligand fragments, conform the resulting peptide chain, and identify the best fit of the ligand into the binding site of the receptor. They identify the conformation of the promising chain using the embedded measurement marks in the form of a set of torsion angles and then report it along with the chain sequence to the analysis module of the software to reconstruct the physical model in silico and evaluate a variety of its properties. Through a user-friendly graphical user interface, and in conjunction with several open source software packages, the user can benefit from the wide range of functionalities enabled by the design and analysis modules. The design module provides high customizability. Examples are customized number, shape, and size of measurement marks, customized range of torsion angles, choice of fine or coarse segmentations of the molecular chain, as well as shape and size of hinges, which is taken advantage of to guide the users toward proper assemblies. The analysis module enables a variety of tasks such as reconstructing the physical model in silico, energy evaluations, as well as collision detection. We have verified through our special test cases that the match between the ligand and template receptor will not occur if the incorrect conformation is used or if the sequence is not right. And it only happens when both sequence and conformation are properly chosen. Our tool has also shown to be capable of generating accurate Ramachandra plots where a great match is observed between the favorable sections of the energy heat map and the allowable conformations obtained from the physical model. The effectiveness of the tool in ranking different complexes has been investigated by quantifying the quality of match between the receptor and the ligand by counting the number of embedded surface marks on the ligand fragments that are in contact with the receptor. Using paint at the binding pocket of the receptor, followed by placing the assembled and conformed ligand onto the receptor's binding site, and counting the colored surface marks for the native conformation as well as for 3 non-native conformations, we observe that the quality of match is directly related to the number of colored marks, with the native conformation taking the highest value. In another test, coarse-grained fragments of a ligand are taken along with the receptor from a real ligand-receptor example to investigate the geometric match at different conformations and orientations. At the native conformation and orientation, good geometric match is observed, while the non-native conformations and orientations result in poor geometric matches. Assemble and match is a powerful tool that not only helps the drug designers but also can give rise to democratizing the drug design practices. Exciting new features are on the way, so stay tuned. For more information, please contact Pouya Tavusi at pouya.tavusi@gmail.com.